This video is a very elementary introduction to the Mathematica package xTensor for doing symbolic computations in General Relativity. If you don't have it already, you have to go and visit the exact page, download and install the software at the appropriate place in your system. So go to the exact page, visit download, and then choose the TGZ or zip file according to your operating system. So my operating system is a Linux one, so I download the first one here. And then all you have to do is to follow the instructions that can be found in this file here, installation notes. And according to the operating system, or whether you have to have a system-wide installation or a single-user installation, you have to take the file that you downloaded and unfold its contents at the appropriate place in your file system. So in my case, I will make a system-wide installation, and I will just go in this place in the file system. So it will become a super user, and then go to this place here. And open the contents of this TGZ file, this tar.gzip file, in this directory here. So when this is done successfully, there is a subdirectory here called exact that has many files, and the package can be loaded in your Mathematica session. So that's all. And if you have Windows, you just have to take the zip file and unzip it in the place that is mentioned here in the instructions. Just make sure that you put the version of Mathematica that you're using here, whether it's 13 or some older one, or if you're watching the video many years from now, higher than 13. So the next thing is to read the documentation and figure how to use the software. It is a complicated package that is meant to be used for large computations. So if you want to do something simple, this is not the package for you. But if you want to do complicated tensor calculations in general relativity, it may pay off that you spend some time and learn how to do these calculations that we will perform together today. So this is the documentation page of exact. There are many packages that come together with exact. This is the core package here, and what we're interested in today is the package xTensor. There are two main notebooks that you have to download and open and read, and that will be very useful for you. And you can either download them from the web, or after making a successful installation, you can find them on your computer system at these locations here. So in order to read them, it is a good idea that you make a copy, a temporary copy, because when you open them with Mathematica, you might run things and change the contents. So always open a temporary copy of those documentation notebooks. So let me make a copy here for the xTensor doc, and then I can use Mathematica to open it, and this is how it looks like. It has several chapters, and if you plan to be serious with xTensor, I advise you that you start patiently going through all those sections one by one. And of course there is a lot of information because xTensor does a lot more things than doing computations for ordinary general relativity, but you should read the sections that apply to the computations that you want to perform. There are also lots of introductory courses that are available from the documentation page of Exact. You can watch videos, or you can get the slides from people that have made some elementary presentation of the Exact software. So find the one that fits best to your needs and dive in and enjoy. So let's start doing some computations. The first thing that you have to do is to load the package. So the package we're interested in is a sub-package of Exact, and it's called xTensor. So this is how it starts. It prints some messages. It is an open source software under GPL. Now, many times computations will go wrong or will get stuck, and you will need to restart everything. So if you want to restart, you cannot just reevaluate the notebook, because you will see there are many definitions that are done by the package, and of course if you read the detailed documentation, you'll find out how to undo all those definitions one by one, but it's usually quite complicated, and a much shorter way is to quit the kernel. So you can give the quit command, and then of course you have to delete the quit command from here and go here, evaluation, and re-evaluate the full notebook and get back to the point where you were calculating. So use quit at any time to restart and re-evaluate all the commands found in your notebook. There is a lot of documentation online which you can access with the usual Mathematica mechanism for getting information. So for example, if you know a function, you can type a question mark, the name of the function, and then shift enter. So then you will get a very brief message describing the usage of this function. If you don't understand, you have to go and consult the full documentation. And if you want to see all the functions that are available from the xTensor package, just ask information about everything this way. Then you'll see all the available functions provided by this package here. And if you click on any of those names here, you will find information about how to use it. But as I have already told you, those messages are very brief, and they do not substitute for reading the full documentation. So the start of any computation is to define a manifold. The manifold is defined by the function def manifold, and in its very elementary usage, we put here 3 arguments. The first is the name of the manifold, so we call our manifold M4. The number after that is the dimension of the manifold, which in our case is taken to be 4. And then there is a list of atomic symbols, 1-character symbols, that correspond to the indices of the tangent space of this manifold. So put here any indices that you want to use in your tensor equations. There are also some functions where you can add and remove indices, but I'm not going to show them to you now. So you better plan ahead which indices you want to use for doing your computations. And that is very useful because with xTensor you can do computations on different manifolds and that have different tangent spaces, and each tangent space may have its own indices. But I'm not going to show you that today. So there are messages that it is quite instructive to read. Def manifold says that it is defining a manifold, M4, that is the name of the manifold, and there is an association of another entity called here, tangent M4, which is the tangent space, the tangent bundle of this manifold. Information about the manifold can be accessed using various functions. Let me show you some of them. So diff of manifold M4 will inform us that the dimension of the manifold is M4, and tangent M4 will tell us that the tangent space of this manifold is TM4. Of course, this is the output form of the tangent space, and if you want to use it as a symbol in expressions, you have to see what is its input form, which is, of course, tangent M4, as we have already been informed in this line here. So you can use this name, for example, to find out what are the indices that are used in computations that involve tensors in this bundle. So you see the indices that we have asked for in our def manifold line here. Now, notice something, that there is the name that is chosen to represent the tangent bundle of our manifold starts with the name tangent, and then it adds the string M4. And M4 is the name that we have chosen for our manifold. So exact is creating a new name, a new head, as it's called in Mathematica, that has that starts with something that is always the same, like tangent, and then it attaches the name of the manifold that we have chosen. And this is done for many other heads that will be representing tensors, covariant derivatives, and other things. So this is part of the philosophy of the programming of exact. Now today we are going to perform calculations there is in the presence of a metric. So we have, if we want to have a metric in our calculations, we have to use def metric to define it. And again, the most basic usage, if we want to have a metric here with an associated covariant derivative CD, which is a Christoffel connection, that means compatible with the metric and torsion-free, then all we have to do is provide those three arguments. -1 here corresponds to the sign of the determinant of G. So if we want to use the Minkowski signature for our metric, this is taken to be equal to 1 in 4 dimensions, of course. So we press enter, shift enter, and you see that there is a lot of work that is done by this function under the hood. So you should read those messages because they give very useful information. So you see that many tensors are defined by the call of this function. So you see that there is a tensor here that corresponds to the metric, which is called G. Then there is an antisymmetric tensor with 4 indices called epsilon G. So you can guess that this is the Levi-Civita tensor for the metric that we have defined. Then the other line that is of interest at this point for us is this one here, and it informs us that a covariant derivative has been defined that has the name CD, and CD is the name that we have chosen to be in this slot of def metric. There is practically no restriction to the names that we put. We can just put cat or dog, and then the corresponding covariant derivative would have the name that we had chosen. You see here that torsion is vanishing with this call, so we have a torsion-free covariant derivative. There is a way to have covariant derivatives with torsion, but I'm not going to show you that in this video. Then Christoffel symbols of Christoffel CD, and again you see here that tensors that are closely related to the covariant derivative have a name that is easily understandable, like torsion or Christoffel, and then they end with the name of the covariant derivative that we have chosen. The same thing is here for the Levi-Civita tensor, although it's not very clear because we have chosen a very easy name for the metric, just to be the character G. But the fact that the Levi-Civita tensor is called epsilon G is because we have chosen the name of the symbol for our metric to be the character G. If we had called our metric to be metric G, then the Levi-Civita tensor would have been epsilon metric G instead of epsilon G. Here you can guess that this is the Riemann tensor associated with the affine connection of the covariant derivative CD, Ricci CD, the Ricci tensor, the Ricci scalar, Einstein tensor, the Weil tensor, TFR Ricci means trace-free Ricci, and other things that we will soon see. And you also see that det G corresponds to the determinant of the metric, and it can be used in expressions, and the fact that it's called det G is again related to the fact that we have chosen the symbol, the character G, to represent the metric. So if we had chosen metric G, then this would have been det metric G instead of det G. So the objects that we will use to do computations are tensors. And tensors have a very simple notation that we will see very soon. But the first thing that we have to do is to define objects that are tensors. And these have a complicated internal representations which fortunately we don't have to know. All we have to do is to use the function def tensor, choose a symbol for the tensor. Here this is the tensor v, and put here the indices that define this tensor in the spirit of the abstract index notation. So here the index alpha is in the set of the indices that we have chosen for the tangent bundle of our manifold. And you see here that the first argument is the tensor with the index that it takes. So this is a vector, v is a vector. And here we have to put the manifold that it is attached to. So when we evaluate this function here, we are informed that a tensor v has been defined. Now, tensors have covariant and contravariant indices, and there is a notation for that it's not probably very easy in the beginning, but you will get used to it later. So we differentiate between upstairs and downstairs indices by putting a minus sign. So when alpha here has no minus sign here, it means that it is an upstairs or covariant index, and if there is a minus sign there, it means that it is a downstairs or a contravariant index. So this line here defines what we call a vector or a 1-0 tensor, and this line here defines a 1 form or a 0-1 tensor. Then we can form expressions involving those symbols. So if you write v of alpha, so in order to write alpha here, I press escape, the character A, and then escape again, and then I have an alpha. Then the input form is quite different from the output form. So exact, in order to make the expressions easy to use, define for those tensor objects an output form that is easier to read. Similarly, if we want to write omega, so escape O, escape, puts here an omega, and then I can put here an index that does not need to be alpha. It can be any index from the set that I have chosen, for example mu. So escape M, escape, puts a mu here, and then I close the list. So you see here that the output is v with index upstairs and omega with index downstairs. So let's define some more tensors to use later. So that is another vector called u, and that is another one form xi. So let's write some expressions here involving those tensors. V of beta, then omega, escape O, escape, minus nu, escape, n, escape, puts a nu here, then u of sigma, escape S, escape, and then xi, escape X, escape, puts xi here, and here minus rho. So minus escape R escape gives us a list of the output forms of those tensors. We can do more complicated, we can give, to our tensors more complicated properties, like a specific symmetry. So this is a 0-2 tensor. F, it's called F, has two indices, downstairs, alpha and beta. It is related to the manifold M4, and it is anti-symmetric with respect to the exchange of those two indices. So that defines this anti-symmetric tensor, F alpha beta. And here is a symmetric tensor, which I call S. So it also has two indices downstairs, and it is symmetric under the exchange of those two indices. Now, sometimes we run out of symbols, so it is a good idea that we are more verbose with the names of the tensors that we choose. So here I have the tensor xTensor, has three indices, one upstairs and two downstairs. It is symmetric with respect to the exchange of those indices downstairs. And look here, I put an option that directs exact how to print this tensor, what is its output form. So this is a script S. You can form it like this: escape, SC, S, capital S, and then escape again. And then you can write expressions with those tensors: minus mu, minus rho, S minus alpha minus delta, and S tensor u minus rho minus sigma. So, since we have not instructed exact how to print the tensors f and s, the symbols f and s are used when in the output form. But xTensor is not printed by using the full input name of this tensor, but what we have chosen here is used there. If we don't want to use a tensor anymore, we can use the function undef tensor to delete its definition. So now xTensor is not available anymore. We can define other objects too that are necessary for our calculations. For example, we can define constants. Maybe you want to define the mass of a Schwarzschild black hole, or here, sorry, you define a symbol h bar that is a parameter in your calculations, and you want it to be constant and not depend on any other variables in your calculations, so that their derivatives, for example, are equal to 0. So h bar can be used in expressions now, and every time that you put it in an expression, its output form is what we have chosen here to be with this print as option. We can also define scalar functions. And these are functions on the manifold, and they have no indices. Okay, so we have seen how to define tensors of any rank and how to put them in expressions. Let's see now how to do contractions. Contractions follow the Einstein convention. So we have to have an upstairs index and a lower index with the same name, like for example here. So V of mu times omega minus mu will give us the contraction of a vector with a one form. Since we have a metric, we can write down the vector v with an index downstairs. This is allowed because we can lower indices using the metric. So this is the norm of the vector squared. And this is another expression where we contract the first index of the tensor S with the index of the vector u, and we have a free index, the second index of S. And otherwise, if all those indices are different, then these are just tensor products. Now let's look at this expression here. We contract f with the vectors v and u, and we obtain this expression here. Now let's do the same thing, but let's put here the vector v. So you see we obtain this result with u replaced by v here, but you remember that when we defined f, we gave to those indices the property of being anti-symmetric. Now this expression, we know that it is equal to 0 because it is anti-symmetric with respect to the exchange of mu and nu, but it is symmetric with respect to the exchange of mu and nu in this product. But we don't see that. So in order to have the symmetry being taken into account and give you a simpler expression, you have to use the function 2 canonical. 2 canonical is the most useful function in the exact system. It takes tensor expressions, and by using internal rules, it puts the expression into a canonical form. Now you read the documentation to see the details of what canonical form is, but in our case, it means this. It gives us a 0. So by putting the indices in the right way and using the symmetries of the function, then we obtain the zero result as expected. So this is a similar situation here, where we contract the antisymmetric tensor F with the symmetric tensor S. Now, this is the result that we obtain. It is not zero, but if we apply 2 canonical to this expression, then we obtain 0. So, many times we make mistakes. And for a tensor equation to be valid in the abstract index notation, either indices have to be different, and they are called free indices, or they have to be the same, and in that case, one has to be upstairs. The contracted indices should be pairs of indices that are, one is upstairs and the other is downstairs. So we obtain a result like this. So suppose in an expression that we make this mistake, what would we see? Well, we see something that makes no sense. So it's a good idea that we validate our expressions. There's a function called validate, and if we apply it on this expression, it would catch the error and tells us found indices with the same name mu, and that is not allowed. Of course, if you use here a different name for the index, then that is perfectly legal, and it can be validate simply returns the result of this expression. So this also is correct, but this is not correct. Similarly, if we write S, this is allowed, although this is a U02 tensor, because we have a metric, we can raise the first index, and that is perfectly fine. But if we had used this expression, that is not allowed, then validate would catch the error and display it. So let's write as examples some more expressions. Let's use the Riemann tensor. And the Riemann tensor has the name Riemann together with the name of the covariant derivative. So by default, as we will describe in a follow-up video, the Riemann tensor has the first 3 indices downstairs and the last one upstairs. And of course, now that we have a metric, it doesn't matter because any index can be raised and lowered, but here I write it in the politically correct way. So I contract all those indices with the vectors and 1 forms that you see, and I obtain the result shown here. I could have put here the same vector v, and that is perfectly fine. Now you remember that the Riemann tensor is anti-symmetric with respect to the exchange of its first 2 indices. So this expression is actually equal to 0 because v nu is symmetric with respect to the exchange of nu and nu, and the Riemann tensor is anti-symmetric. But in order to see this, I have to apply the function to canonical. And then xTensor gives us the correct result, which is equal to 0. So let's work out a similar example. So here you see that I use the contravariant Riemann tensor. All 4 indices are downstairs. This is the output form of this expression. But the contravariant Riemann tensor is also antisymmetric with respect to the exchange of its last 2 indices. And here you see that I have contracted it with a tensor that is symmetric under the exchange of those indices. I can see that again by applying the function to canonical, and I obtain 0. The Riemann tensor has more complicated symmetry properties. One of them is that it is symmetric under the exchange of the 2 pairs of indices, mu and lambda sigma, and lambda sigma mu gives us the same components of the Riemann tensor. So I'm writing here an expression that you can easily see that it is 0 because of using this property. So f is antisymmetric, and I contract its indices with the first and third index, and then the u squared term is symmetric under the exchange of mu and sigma, and their indices are contracted with the second and fourth slot of the Riemann tensor. So let me write down this expression. This is the result. And although you see that I have to play a little bit with the symmetries to see that the result is 0, xTensor will do it immediately when we apply the function to canonical. That is another example here. So here I contract the Riemann tensor with the antisymmetric tensor f, and the indices mu and lambda are contracted as before, and then I use the Ricci tensor, which is symmetric under the exchange of sigma and nu, and I contract it with the slots 2 and 4. So that is a similar situation to the one that we have computed in the previous cell there. So you see the output form of the Ricci tensor. Same symbol is used here. The nabla is the symbol of the covariant derivative by default. You can change that if you like. And we can see that this expression is 0 by applying to canonical. Now sometimes we have more complicated expressions that we want to use the power of the simplification routines of Mathematica as well. So there is a function which is called simplification. Which basically what it does is to first apply to canonical and then the simplify function of Mathematica. So when xTensor starts, independently of whether we have a metric or not, it defines the Kronecker delta symbol that can be used in tensorial expressions. So we have the simple Kronecker delta, delta mu nu, but we also have the generalized Kronecker delta, which they are symbols that have antisymmetric products of the Kronecker delta. So the symbol used for the Kronecker delta is delta with a small d in the beginning, and then G delta with capital G is the symbol for the generalized delta symbol. And we can expand an expression involving generalized Kronecker deltas using the function expand G delta. So let's play a little bit. Let's start with the simple Kronecker delta. So this is how you can use Kronecker's delta in a tensorial expression, and xTensor knows that its trace is equal to the number of dimensions of your manifold. In our case, this is equal to 4. So you can use the indices of the delta symbol to contract the indices of tensors in any manifold, like the one that we have defined, the manifold M4. So now the upstairs index of the delta symbol is contracted with the index of the one form, omega, and that will give us omega mu. Now, let's look at an example of a generalized delta. So it has two lower indices, mu and nu, and two upper indices, rho and sigma. So this is its output form. But we can use expand delta to have a more explicit expression involving simple Kronecker's deltas. So let's add more indices. So that is delta with 3 indices upstairs and 3 indices downstairs. And this is how it looks when you expand this expression here. Now, in the case that we have a metric, we can lower some of those indices. So we can put here an asymmetric number of upstairs and downstairs indices. And in that case, we will start seeing factors that involve the metric, which has been used to lower the index. So here, this is valid, and this is valid as well. Now, if there is no metric defined, then this expression would have been wrong. Now, let's look at the Levi-Civita tensor. So it has 4 indices. And you see how it is printed, what is its output form, has a real epsilon, and then the name of the metric, G, is attached to it. So if you change this name, this will change as well, and you see the indices here, alpha, beta, gamma, and delta, that appear downstairs. So you can write now tensorial expressions. Let's write one that we know that it is equal to 0. This is a totally antisymmetric symbol. Tensor, sorry, it's not just a symbol. So it is antisymmetric with respect to the change of alpha and beta, but the metric is symmetric. So this is the inverse metric, of course. And if you want to see that this is actually equal to 0, then you have to use two canonical or simplification. And this is indeed equal to 0. You can write contractions involving products of epsilons, like this one. So you see here, we contract one index, the last one, minus delta here, delta there, and then the free indices are all downstairs. So you see that we obtain a result that involves the metric. If we use the inverse Levi-Civita tensor here, we will obtain deltas instead. So let's contract more indices. Now the expressions are simple, but of course lots of calculations have been performed to arrive to this result. Contract three indices, beta, gamma, and delta. And then we contract all four indices to obtain n factorial, where n is equal to 4. Now, this is very useful because many times we have expressions that are even more complicated with products that involve more than one epsilons. So this is an example here. So as you know very well, the metric is used to raise and lower indices. So let's look a little bit closer to how those contractions work. This is a very simple example. We take the metric and we contract one of those two indices with the inverse metric. So xTensor knows that this will give us a Kronecker delta. Similarly, if we take the trace or contract both indices, then the result is 4. This is another example here, where we contract both indices. That is the same as the one before. So let's use this to raise and lower indices. So I have the vector v as an index upstairs. I contract it with the index nu of the metric, so that should give us v with the index nu lowered to v mu. But you see that this is not done, so I simply get this expression here. If you want to actually perform the contractions, you have to apply the function contract metric. And then you see that the result has the vector v with its index lowered correctly. Similarly, we can use the inverse metric to raise the index of the one form, omega. Now, this will give us a product like before, but if we apply contract metric, then the index of the one form is raised. So we can raise one index of the antisymmetric tensor F. Again, we have to apply contract metric. This is a different contraction. So we take F times omega and we contract nu with sigma. So contraction gives us the product F omega with indices appropriately placed. Now this gives us this, and the metric contraction gives us the two indices raised. Same with the tensor S. Contract the two indices here to obtain the trace. Let's apply contraction on the Riemann tensor. So I take the Riemann tensor and I contract nu and sigma. So this is the result. But now contract metric will not simply give us the indices up and down, but this is equal to the Ricci tensor with a minus sign. Similarly, if we take the Ricci tensor and contract its two indices, we obtain directly the scalar curvature. Now let's look at the covariant derivative that comes with the metric. Now before we do that, let's also define some scalars, some functions. So f here is a function on the manifold, and phi, you see it's defined again as a tensor with no indices, but there is no manifold attached to it. That is a sign that this scalar here is covariantly constant. We also define a constant symbol, G Newton, which we ask that it is printed in this simple way. So now if we write F, G, and G Newton, this is the result of the output. So for any manifold that we define, there is a predefined connection, which is the ordinary flat, sometimes called the partial derivative connection. This is a connection that can be defined only locally in a coordinate patch. It is flat, and that means that it commutes when it acts on objects. So the symbol for this connection is PD, from the initials partial derivative. So when it acts on a function, it gives you the partial derivative of that function. When it acts on a vector, notice here that there are two groups of square brackets. The first group here has the index with respect to which we are differentiating. That is the mu that is found there. And then the other bracket has the object that is differentiated, which is it should be a tensorial expression. So that is d mu b nu. The product rule for function times vector is built in, and the Leibniz rule is applied every time we have the product of a function with a vector, or in fact with any other tensor. And the same is true if we have tensor products, like here a tensor product of two vectors u and v. So again, the Leibniz rule is applied in the output. Now, I have promised you that the action of the derivative operator PD commutes. So I'm writing here an expression where d nu and d mu are compared when acting on a vector. So you see that this does not evaluate to 0 unless we apply the function to canonical. And then we see that this action is commutative. So now let's look at the covariant derivative associated with the metric. So this is an example here. The syntax is the same as with the partial derivative, except that we use the name of the covariant derivative, which in our case is CD. This is the index of the covariant derivative, and this is the expression that will be differentiated. So that gives you, again, d mu d nu. And you can apply this on a one form, for example. So let's write down here the omega one form. And that gives you d mu omega nu. And you can apply this on tensor products like V rho. And you see that the Leibniz rule is applied on the products. And this can be any tensor, like for example, a scalar f. Now, you have noticed that the action of the covariant derivative on the function does not change in the output form. The symbol nabla is used. If you want to convert this to the partial derivative, as you know that any covariant derivative, when we compare it to the partial derivative connection, then the actions of any covariant derivative on a function is the same as the partial derivative connection. So you have to apply the function covariant to Christoffel. So there's also a D here, covariant derivative to Christoffel, and that will change the nabla symbol to the partial derivative. So the nabla here so that is with the covariant D to Christoffel function acting on the expression and without it. So you can see how the derivative operator acts on a constant. That gives us a 0, as expected. Now, scalar multiplication is built in. So G Newton, you see it's printed as Gn, is known that its derivative is equal to 0, and it's taken out from the derivative there. And the same would have been true if you had used, let's say, the number 7. Or if you multiply a vector by a constant, then the derivative here is multiplied by this number. Now, we can apply this to higher rank tensors, like F. Or products. And obtain more terms like that. So we can always expand an expression that has the covariant derivative of a tensorial expression to an expression that involves the partial derivative and the Christoffel symbols. And that is done by the application of the function cov d to Christoffel. So let's take the action on a vector, like we have already done, and then apply the function cov d to Christoffel. So you see here that we have an expression that looks familiar, has the partial derivative, and then the correction that is done by the Christoffel symbols. But you see here that there are those funny indices that for them to have unique names, xTensor adds those funny dollar numbers. So if you don't like this ugly expression, you have to use the function screen dollar indices, and then you will obtain a prettier looking expression that has simply the index alpha contracted here with the index of the Christoffel symbol. So you can also put a 1 form, and then you see we have the correct sign, or a higher rank tensor. And we have those two correction terms, one for each index. And if we have covariant indices, we have a similar expression like this one. Now, the Christoffel symbols have their own input form. The head used for them is Christoffel followed by the name of the covariant derivative. So every time we put such a symbol in a tensorial expression, we will see in its output form this notation here. And of course, now that we have a metric, we can raise and lower indices using the metric and obtain similar things here. Now, for the particular connection, which is compatible with the metric and torsion free, we have an expression of the Christoffel symbols in terms of the metric. In order to obtain this expression, we have to apply the function Christoffel to grad metric. So again, this is a familiar expression, but ugly looking due to the dollar indices, which we can make them disappear by applying the function screen dollar indices. And that is the familiar expression that gives us the Christoffel symbols in terms of the metric. And if we put this index downstairs, we obtain again this familiar looking expression. So let's see how the covariant derivatives can be expanded in this form. So let's take the covariant derivative of a vector. First, we have to apply the function covd to Christoffel, obtain this ugly looking expression. Make the dollars disappear. And then, if you want to have an expression in terms of the metric, right after the covd Christoffel, we add the Christoffel to grad metric. And then we have this result here. And we can further manipulate this expression by applying to canonical. And then this expression is expanded and put in canonical form. Now we can do that for a more complicated expression, like f minus rho. Then let's contract the index nu. So that gives us this expression. Only the Leibniz rule is applied, nothing else. And then we can apply this whole train on this expression to find this simple expression here. Now, these messages here can be ignored. They come from two canonical. They detect that this connection here is incompatible with the metric, because of course d mu g is not equal to 0. But by ignoring those messages, we see that the final result is here. So you see this term with the Christoffel symbols. This appeared because of the use of two canonical. If we remove this, we have an expression that has no Christoffel symbols. So many times we have to differentiate a tensorial expression more than once. So maybe here we have to take another derivative, CD minus rho, and then this is put inside square parenthesis, and then again CD minus sigma that's the third derivative, etc., etc. So for some people's taste, these are too many brackets and it can be confusing. So let me show you another way to write those expressions by taking advantage of the symbol at of Mathematica. So that means that this function is applied on this expression. So you see that this has the same effect as this. And then it is easier to write expressions with more derivatives because all we have to do is to apply this as many times as we want. So and then we can do monstrous stuff like expanding this to Christoffel, and then to metric, blah blah blah. Well, we obtain quite useless output here, but you can see where I'm going. So, well, let's be more humble and consider twice differentiating this vector field. Then we put in the Christoffel symbols. Oops. And then manipulate the expression to the level that we want. Now this is another example here. Let's compute the derivative of the tensor product of U with the derivative of S. So you see the Leibniz rule is applied. Then we can put Christoffel symbols in the expression. And, well, I don't know if you want to do that, but you can. So you see here we have a big expression that has more indices than we have in our tangent bundle, so we cannot avoid the fact that there are extra indices introduced by xTensor like delta 5, delta 15, delta 12, etc., etc. Lead derivatives are also available with the xTensor package. We can take the lead derivative of the vector u in the direction of v using this expression here. You see the output form is easy to read. So v here is the vector with respect to which we are differentiating, and here we put any tensorial expression that we might like to differentiate. So you can add here, let's say, the tensor and the Leibniz rule is applied. So here is another example using the anti-symmetric tensor that we defined before. And the useful functions that can be applied and give us expressions in terms of the covariant derivative is like, for example, Li d to cov d. And that gives us the result in terms of the covariant derivative, partial derivative. So that is a familiar expression. If we just put a vector here, that gives us the Lie bracket of v and u. So you see that's v du, v and u dv, minus u dv. So when the lead derivative is expanded, the PD connection is used by default. But there is a way to use Li d to cov d to give you this expression in terms of the covariant derivative CD. So then you have to use the function this way. The first argument is the lead derivative that you compute, and then this tells Li d to cov d that you want the expression in terms of CD. Again, we have to screen the dollar indices and obtain this expression here. So you can do that with any tensor. Now, as we have already seen, the lead derivative knows the Leibniz rule. And you can put here our scalar f as well. So, in order to substitute the action of the lead derivative of a function, then of course you have to use Li to cov d to see that. So you see now that LVF has been replaced by DF. You can use vector expressions for the vector with respect to which you are differentiated for. And the basic properties of this, like linearity, is applied here, so that is Lev plus 7 times Gn Lu. And if you put here the function f, well, that's all it knows. So you know the Lie derivative is closely related to the Lie bracket of two vector fields. And in fact, we saw that here, where we obtained the expression that is the expression that gives the components of the Lie bracket of two vectors in a coordinate basis. So if you want to compute the Lie bracket of two vector fields, you have to use the function bracket. Then the first bracket here has the two vector fields that are, well, bracketed. And here you have to put an index that will be used for the resulting vector field. So again, there are functions to expand this expression like you do with the Lie derivative. Now the function that makes the transformation instead of Lie d to cov d is called bracket to cov d. And you see that we obtained the expression here. Well, in the other way, of course, because this is the Lie bracket of v and u, and here we have put u and v. You can also expand the Lie bracket in terms of another covariant derivative by using two arguments in the bracket to cov d function. The first argument is the bracket, same syntax as before, and then the second one is the covariant derivative. And then you obtain an expression that involves the covariant derivative. So linearity is known and applied. So a vector plus a constant another vector gives us the bracket of the vector plus the constant times the bracket of the other vector. And here, if you put a function that multiplies the first vector, then the Leibniz rule is known and computed. Okay, let's do something more interesting as an exercise. Let's prove this identity. This is quite easy to prove analytically when we know that the Lie derivative of a vector field with respect to another is equal to the Lie bracket. But let's see how we can do manipulations to expressions with the available functions from xTensor to prove this result. So let's start with the left-hand side. So what we want to do is to compute the Lie derivative with respect to the Lie bracket. So the bracket here is put in the first slot of Lie d. That's the vector field with respect to which we are differentiating. And then xi is the vector field that we differentiate. So this is the result. So the first thing that we will do is to write this in terms of the covariant derivative. So we apply the function bracket to cov d to this vector. So bracket to cov d is applied to this bracket here, and we specify that we want the expression in terms of CD. Let's screen the dollar indices so that we don't see something very ugly, and that is the result that we obtain. So the next thing that we want to do is to expand the Lie derivatives in terms of the covariant derivative. So let's save this expression into the variable equation 1. Let's also screen the dollar indices. So EQ1 now is this expression. Now let's now go to the left hand side. So we take the first term, so that is LULVXC. So that is differentiating twice C, first by V and then by U. That is the second derivative. And then let's expand this expression with respect to the covariant derivative CD. We obtain this. Let's save this into a variable called equation 2. So equation 2 now is this expression. Now let's take the second term of the right hand side, which is again differentiating twice but with the opposite order. So this is what we want to do. Before we had LULVXC, now we have LVLUXC. And then we expand everything with respect to the covariant derivative CD and save that into a symbol called equation 3. So in order to show that this is 0, we want to show that this is 0, all we have to do is to show that this minus this is equal to 0. So what we have to do is to form the expression equation 1 minus equation 2 plus equation 3. And that is all the mess there. So the first thing that we will try is to apply simplification. And we see that this expression has been simplified considerably. Now we start seeing why this is equal to 0. We see that in those brackets here we have the covariant derivatives but in the opposite order. So what we have to do is to tell xTensor to commute those derivatives so that this will be the same as this one. So what I will do is first save this into equation 4. So equation 4 is this, and then I will compute this expression here. So I will discuss this function quite a lot in a follow-up video, but it's called commute covariant derivatives. So what it does, it takes here an expression that involves covariant derivatives. We have to tell which covariant derivative we want to commute, and these are the indices that we want the result to be in its final form. So here that we have the indices in the opposite order, what it will do is it will commute those derivatives, and then the price to pay, of course, is to have Riemann tensor terms. So you see this expression here, and we can define equation 5 to be this. And then we can simplify and save the result in equation 6 using simplification. And now you see that all that we have here are those three terms of the Riemann tensor, and you see that they are added with respect to all permutations of the lower indices. So simplification has made, has put this as a common factor, and then we see from here that this result is 0 because of the properties of the Riemann tensor. Unfortunately, there is no function in xTensor to apply those multi-term symmetries that the Riemann tensor has. So the rest we have to do it by hand, and then maybe next time I will show you how to define rules that you want to be generally applied to your expressions so that they force such symmetries. But let me now do it by using a brute force method. So I'm doing a simple substitution here in this expression, and I take the first term, which is Riemann CD rho alpha beta gamma, and replace it by its equal. So I take the symmetry relation that says that the antisymmetric part of this expression is equal to 0, and then that means that rho alpha beta gamma is minus rho gamma alpha beta plus rho beta gamma alpha. Well, we are almost there, but we already see that those two terms cancel. But now the application of two canonical will give us 0.